Hey guys, I know that you are probably a little nervous after last week and those horrible related rates problems, but I assure you that today's problems are going to be much better than they were last week. What we're doing today is popularly known in the math world as a sliding ladder problem. And they call it this because, well, that's how this problem's going to begin. We're going to pretend that we have a wall, and that's going to be the ground, and it's almost straight. And against our wall, we're going to prop a ladder. And the idea is that maybe the ladder begins to slide down the wall. So as this is sliding down, this part over here is going to be sliding out, and that makes sense. And I know that you really, really want them to be sliding at the same rates and the same speeds, but guess what? They're not. So that's why this math exists. So what we're going to do is talk about the setup of this, and of course the calculus approach to doing it. So just like last week, it's always good to first have some kind of a formula that we start with, and then from our formula we're going to take a derivative and all that good stuff. So what formula might we use? Well, when you just look at this problem, ignoring the fact that that's not really a ladder, not really the ground, and not really a wall, if you focus right here, kind of looks like a triangle, maybe, kind of, I hope so, and a triangle formula that you've known for a very long time might be the good old Pythagorean Theorem. Here we go. Let's see if I can. There we go. And and that needs a squared. So we've got our Pythagorean theorem, and of course your C just needs to be your hypotenuse, and you've got your A and your B. And depending on what's given to you in the problem is, of course, where you're going to plug stuff in. Are they giving us a distance on the ground? Are they giving us a height on the wall? In the first example we're going to do, I'm going to give you guys the following situation, and I'm going to type it so it's not nearly as horrible. Okay, so let's pretend that you're asked to do the following. A ladder that is 10 foot long is sliding, let's see if I can type, sliding down the wall at a rate of, maybe it's going to be 3 feet per second. That's actually quite fast. Find the rate that the ladder is sliding away from the building when the ladder is, let's think, 4 foot from the ground. Alright, so this is a decent problem here. And it's going to start off actually quite nice, because since we do know the length of the ladder, if you remember from last week, if there is a constant in the problem that's not changing, you do get to plug that in first. So if 10 foot is how long our ladder is, then by golly, let's label our ladder as 10 feet long. So I know that that is 10 foot long, okay? And going along with last week, we also want to label the other things that we know. Now, if it says that we're sliding down the wall at a rate of 3 feet per second, well, sliding down the wall, I guess that would go there. And since it's going down the wall, I'm also going to call that a -3. Now, that's not a distance, that is a rate. So let's be very clear about that. I guess the notation it would need is how fast it's sliding down. We need d something over d something. Let's do this. Instead of A's, B's, and C's, I'm going to change this into X and Y, only because we can think of it as being on an axis, and that might be easier for some people. Mainly me, easier for me, so we're going to do it. Okay, so if I think of this as my x and this is my y, and those are the legs of my triangle, then I would actually call this my dy over dt. We're doing everything with respect to time. So my dy over dt is a negative 3, okay? And that's how we're going down the wall. What else can we label? Find the rate of the ladder sliding away. Okay, so that's the only thing that we know that's constant at this moment in time. This is the what are we trying to do, so we don't need to plug that in yet, okay? Let's look at this equation and plug in the only constant, which in this problem is the length of the ladder. So I'm going to begin with the equation, what's happening here? Okay, x squared plus y squared equals 10 squared. Okay, that is my constant because that's the length of the ladder, the only thing constant. And then if we're trying to create rates, just like last week, you're going to take a derivative. So 2x dx dt plus 2y dy dt is equal to 0, big fat 0, so I guess that 10 doesn't really matter. Okay. Now it's time to decide what can we plug in and what are we actually searching for. So let me see. This wants to know the rate the ladder is sliding away. So the rate the ladder sliding away is going to be this arrow right here, which is definitely this. This is the unknown. So that tells me I should be able to plug in for everything else and get an answer. So let's start plugging. All right, I'm going to recopy my 2. Now, what's going in the spot of x? IDK. I do know that. I don't know it, but I do. They did not tell me what that x is. But if we look up at our problem, and this is telling us the ladder is 4 foot from the ground, that 4 is actually going to be the distance on the y. That's how far or how high it is from the ground. I know that this is a 10. Why can't I just use Pythagorean Theorem and figure out that distance of x? I think we can. So we're going to be doing a 4 squared plus x squared equals 10 squared. And from here, x squared would equal, what is 100 minus 16? I hope it's 84 because that's what I'm going to do. And then I'll take the square root of that and whatever. It's ugly. I'm sorry. I made this problem up, so you know it's ugly. Okay, so square root of 84. I'm sure that breaks down and gets pretty, but I don't really care at this moment in time. I'm just going to plug in square root of 84 and see what happens. Maybe things get pretty, maybe not. Square root of 84. Okay. Times dx dt, which we don't know. So I'm just going to recopy it. Okay. Plus the 2, recopying that 2. The y is 4. That's how high we are off from the ground. And then the dy dt, that would be that rate that we copied down at the beginning. So I'm going to plug in a negative 3. And now, guys, all you got to do is solve that. So I'm going to stop talking, and I'm going to solve, and you do the same, and let's hope we all get the same thing. Okay, so I'm just going to leave it as 12 over the square root of 84. Pretty sure that that math is right. And then you can simplify that if it makes you feel better. You can rationalize it if it makes you feel better. I don't care. I'm going to leave it like that. And this was a rate, so you need units. Don't just go with feet. This is going to be the same units as the other rate, so we're going to go feet per second. Awesome. So if you turn that into a decimal, you can compare it to the rate that the ladder is sliding down the wall, and you can start playing that game of which one's faster. You know, this is negative 3 or 3 feet per second, and that's going out at a rate of 12 over the square root of 84. Let's see, that's going to be close to 9, and 12 over 9 is definitely less than that. So that is sliding out slower then that is sliding down the wall. So the sliding ladder problem, very famous in the math world. You can apply this Pythagorean theorem to all sorts of situations, really any situation that looks like a triangle, a right triangle, and yeah, it's a lot easier than volume, in my opinion. So hopefully that made sense. We will let you try a problem and then take a break after this problem, and then I'll come back and work it for you. So let's see, I guess start video 2 to get your problem to try, and then I'll help you through it.